So good afternoon everyone and welcome to this lecture. We are we have dealt with the electric lines of force and we are now into electric flux. In the last class we had seen the properties of electric field lines, how they are and how they are drawn. A tangent drawn gives us the direction of electric field. The number of field lines which are coming from a charge tells us how big the charge is. If the field lines are more dense, then it tells us that the electric field is more. We will just continue that concept with this concept of flux or Gauss law. Now, before going on to Gauss law, we must understand the concept of area. And in physics, area is taken as a vector quantity. So that is the first thing that you must remember about an area. When we talk about area in physics, area in some cases, in some scenarios from now onwards, this area will be taken as a vector quantity. This area, whenever we come across area, it will be taken as a vector quantity. Now, if it is a vector quantity, it must have two things. It must have what? It must have a magnitude, it must have a direction. Now, all of us know the magnitude of area. You can find out the area of anything. You can find out the area of a circle. You can find out the area of a triangle, rectangular, square. That is what you all need. Area of a trapezium on the higher side. You can easily find out the area. Magnitude of area is the geometrical area that you all know. Now, the only new thing that comes here is the direction of area or the direction of area vector. Let me write this area as area vector. Now, what do you mean by the direction of this area vector? The direction of area vector is taken perpendicular to the area. So it is taken perpendicular to the area. That is only the new thing that you have to understand. For example, if this is a small area, small segment, you draw a line which is perpendicular to it, ds, S standing for surface, or dA. This would be the area vector of this. When I say perpendicular, if I talk about this surface, this is also a surface, this is also an area. Now, if I talk about the area vector of this area, you can find out the area of this you can find out the area of this square. So that is the magnitude. To find out the direction of area vector, you just take a direction which is perpendicular to this. That is the direction of area vector. If the area is like this, this is the direction of area vector. For this surface, this is the direction of area vector. For this surface, this is the direction of area vector. For this surface, this is the direction of area vector. For this surface, this is the direction of area vector. So the direction of area vector is just perpendicular to the surface. Do we understand this? Yes or no? Okay, but when we talk about perpendicular to the surface, there can be two directions which can be perpendicular to the surface. Let me show you one more diagram, and that will make you think more clearly. For example, if I have this cylinder, now cylinder has a curved surface and cylinder has two circular, what you should say, caps or cups. Now, the area vector for this surface, as I told you, for any surface, it is perpendicular to it. Now, if I talk about these circular parts, this area vector of, let us say, this pink, let me color it pink. The surface area or area vector of this pink one, now it can have two directions. It can have two directions. What are the two directions? The one direction is which is shown by this green. This could be perpendicular direction. The other direction could be just in the opposite direction, this brown one. Both of these directions are perpendicular to this area. Now the question is which direction you will take. Now, which direction you should take, that is again a controversial, that is again a very subjective thing. To understand which direction you will take, we will have to understand that there are two types of surfaces that we are going to deal, or two types of areas that we are going to deal. Let's not call it area, I should call it surface. So we should be dealing with two types of surfaces. One is known as a closed surface. One is known as a closed surface, and the other one is known as an open surface. Now, what is a closed surface? A closed surface is a surface which encloses a volume. So, a closed surface is any surface that has a volume, that encloses a volume. This box, this is a box, and this is a closed surface. This box is a closed surface. It has a volume. You put something inside it, it does not just fall. It cannot fall. You can hear it. There's something inside it. It cannot fall. This bottle is a closed surface. There's water inside it, cannot fall. It encloses a volume. This is a closed surface. So if I start from any point on the surface, I will just remain on the outer side. I cannot get inside this. You understand what I'm saying? This is a closed surface. It encloses a volume. If I open this, now it becomes a open surface. If I start here, I can get inside this. That means this is now an open surface. This surface encloses a volume. This is a closed surface. But if I now do it like this, if I now try to do this one, water is going to fall out from here. That is a closed surface and an open surface. Do you understand? Closed surface.
Yes, sir.
A wardrobe which is closed is a closed surface. A wardrobe which is open is an open surface. A room which is closed is a closed surface. A room with the door or the window open is an open surface. Do we understand this?
Yes, sir.
Now, for a closed surface, the area vector is always taken as outward normal. Outward normal. Here, this is the outward normal. This green side is the outward normal. It's going outside. For this surface, it is a closed surface because, as you can see, it encloses a volume. Something is inside, cannot fall. This is a closed surface. So for any closed surface, the area vector is taken as the outward normal. You understand this? This is an open surface right now. Your table is an open surface. So for an open surface, you can take any normal as the area vector. Doesn't matter. An open surface is an open surface. Both directions are perpendicular. But for a closed surface, outward normal is the direction of area vector. In most of the cases, the direction of area vector would be given to you, so you don't have to worry. But you just have to remember that for a closed surface, what is the direction of area vector? Outward normal. So this is a closed surface. If this is the area vector will go like this. For this surface, it goes here. 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 For this surface, it comes here, 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 here. Do we understand it?
Yes,
That
sir.
is the direction of area vector. For open surface, they will tell you beforehand what is the direction of area vector because both directions are taken as direction of area vector. But for a closed surface, the outward normal is the direction of area vector. Will you remember this?
Yes, sir.
Open surface, the only thing you have to understand, it has to be perpendicular to the surface. So note it down, I'll give you 2 minutes.
Done, sir.
You have noted it down?
Yes, sir.
Okay. Now, this closed surface is the surface which you must remember, because this closed surface is going to come a lot of times in this particular chapter. Do we understand this? This closed surface, you will have to understand. This is what this particular section is all about, closed surfaces. Now, we understood what is area vector. Now, to understand what is area vector, then comes the next heading, which is electric flux. So write the next heading, electric flux. What do you mean by electric flux? Electric flux. So basically, what do you mean by electric flux? It is a measure of total number of EFL. What is EFL? What is EFL? It is not English Football League. What is EFL? Electric field lines. It is a measure of total number of electric field line passing normally through the surface. It is a measure of the total number of electric field lines which are passing through the surface. How many electric field lines are passing through the surface? Normally, perpendicularly. That number is known as the electric flux. Do we understand this?
Yes, sir.
What type of quantity is electric flux? It is a scalar quantity. Electric flux is a scalar quantity. And this electric flux is denoted by the letter phi, the Greek letter phi. Electric flux is defined by this Greek letter phi. And how do you find out the electric flux? The small amount of electric flux which is passing through any surface is given by E dot ds, or the total flux passing through the surface is integral of E dot ds, or you can write it as integral of E into ds into cos theta, where what is E? E is the electric field, ds is the area, ds vector is area vector. Do you understand ds vector? And what is this cos theta? If I say that this is my area ds, ds vector, E is the direction of electric field, theta is the angle between electric field and area vector. Do we understand this?
Yes, sir.
So it is the integral of E into ds into cos theta. If electric field is constant, which will be the case in most of the cases for you, you can write this flux as E into ds ka integral will be S, the area, multiplied by cos theta. Do we understand this? Give you 2 minutes to note this down.
Done, sir.
We have noted this down.
Yes, sir.
Now, you can draw this diagram also if you want to. I will show you the diagram. If you want, you can draw this diagram as well. I had drawn the smaller version of the diagram. You can draw the bigger version of the diagram as well. Here, this one. If you want, you can draw the bigger version of the diagram as well. Now, electric flux. You must remember its SI unit. You can call it as Weber, or you can call it as Newton Coulomb per meter square.
Sir.
Okay, Newton meter per Coulomb square. Remember the SI unit. Remember the Weber. Okay, so electric field is the number of electric flux. Phi is the number of electric field lines which are passing normally through any given area. Right? Do we understand this?
Yes, sir.
It is a scalar quantity. It can be positive, it can be negative, and we will see when it will be zero. So just note this down. Let me know, then we'll come, then we will move ahead.
Done, sir.
Okay. Now this electric flux, as you can see, it's a scalar quantity. So it can be positive, it can be negative, or it can be zero as well. Now we can see the different cases here. For example, when it will be positive, when it will be negative, or when it will be zero. Electric flux in the simplest case is given as this, Es cos theta. Now, whether it is positive or whether it is negative depends on the value of cos theta, right? If cos theta is positive, flux will be positive. If cos theta is negative, flux would be negative. That means if theta is acute, if theta is acute, flux is positive. Do we understand this?
Yes, sir.
If theta is obtuse, flux is going to be negative. If theta is 90 degrees, flux is going to be zero. Now this positive flux can also be called as outgoing flux. This negative flux is known as incoming flux. Outgoing and incoming, this is one way to understand this. You can understand it in this way. This is outgoing. Electric field lines are going away. It is outgoing flux. Electric field lines are coming in. This is incoming flux or negative flux. Do we understand this?
Yes, sir.
Note it down. Let me know once you're done, bacha.
Done, sir.
Boys, are we done? Yes or no? Can't hear you. I hope you have said yes. So that was incoming and outgoing. I will also draw a diagram for you to understand it in a better way. What do you mean by incoming or what do you mean by outgoing? For example, if I have your electric field lines like this, it is going in this direction. Now, if your area vector lies here, ds, or it lies in the green zone, if it lies in the green zone, this is your green zone. If it lies in the green zone, then if it lies in your green zone, then your flux is going to be positive. Do we understand this?
Yes, sir.
If it lies in this zone, if your area vector comes here, ds vector, or it comes here, ds vector, in this blue zone, if it comes in this blue zone, then your flux is going to be what? Then your flux is going to be negative.
Negative.
If your area vector goes like this, red zone here or red zone here, then in both the
Zero.
cases, your flux would be Do we understand this?
Yes, sir.
Here, your theta is acute. Here, your theta is obtuse. Here, your theta is 90 degrees. I hope we understand it. Have you written this?
Yes, sir.
Boys?
Yes, sir. Sir, am I audible?
Yes, beta. Have you done this?
Yes, sir.
Okay. So we have seen when the area, when your flux is going to be positive, when your flux is going to be negative. Now we come to special case where your angle is 0. That means your electric field is normal to the surface. In this case, bacha, your angle theta is actually 0. Do we understand this?
Yes, sir.
In that case, your flux is going to be maximum E into S. Do we understand this?
Yes, sir.
You can draw this diagram and write this. Write this case. Have you written this? You can also write this case, case number 2. In this case number 2, your electric field is parallel to the surface. In that case, actually, your theta becomes 90 degrees or grazing angle. And in that case, your flux becomes 0. Do we understand this?
Yes, sir.
Your angle is 180 degrees, exactly opposite. Then your answer will be minus E into S. Do we understand this?
Yes, sir.
Give you 2 minutes to note this down. Have you noted it down?
1 minute, sir. Done, sir.
Okay. Then this question, a point charge Q is placed at the corner of a square of side length A. To find the flux through the square. What would be the flux through the square? How will you do this? Give you 2 minutes. Solve it. Yes. What is the answer for this one? No one has any answers? The answer is 0. The flux through the square is 0. Why is it 0? Why is it 0? If you look at the electric field line, because of this point charge, the electric field line will
90
go like
degrees.
this. Yes, electric field lines will go along the surface. The area vector of this square is perpendicular to this. So the angle theta is 90 degrees. And therefore your answer is 0. Flux through this side is 0. Flux through this square is 0. Do we understand this?
Yes, sir.
Why were you not giving me the answer, sir, then? Okay, one more problem. An electric field is given by 2I plus 3J, and the area vector is given as 3I minus 4J. All are given in vector form. Find the flux of this electric field. Find the flux of this electric field. I hope everyone is paying attention. Everyone is trying. This one, simple question. These are the type of question that you can expect. I'll give you 2 minutes.
Sir, -6.
Yes, bacha.
-6.
+6 -6.
-6, sir.
-6, sir. That looks like a correct answer, sir. That looks like a correct answer, everyone. What about girls? Did you get it?
-6, sir.
-6, sir. Correct, sir. Everyone got it. So I thought that was a tough question, but you have proved me wrong. Good. Answer is -6. Minus means is it incoming or is it outgoing? It would be incoming. So how do I get this flux? I just need to take the dot product of E with A. Yes or no?
Yes, sir.
So remember, I will get dotted with I. 2 into 3 will become 6. J will only get dotted with -4J. So it is -12. 6 minus 12. And the answer is -6 Weber or units, whatever. And that is your answer. Do we understand this, everyone?
Yes, sir.
Well done. Then this question awaits you. Let's see if you can do this one. It's a simple question. Same question, but here instead of giving the area in terms of vector, they have given the area in terms of explaining something. I'll give you 2 minutes to solve this. Yes, trying.
బీజీ కడుగు దొరికితే మళ్ళీ పెంట్ అవుతుంది అబ్బా మొన్న రాంబాబు సార్ ఉన్నప్పుడే
Well, bacha, shall I do it? How are you supposed to do this? It's very simple, beta. See, your electric field is given in the vector form. Your area is given as 0.2 meter square. It is given parallel to y plane. Now, from there you can find out it is given parallel to YZ plane, beta. Remember, it is given parallel to YZ plane. See, this is your X, this is your Y, and this is your Z axis coming outward. Your plane like this in this YZ plane. Your plane lies in the YZ plane like this. So it is parallel to the YZ plane, bacha. So its area vector will lie along which axis?
Sir,
Yes, beta.
0.24 into 10 to the power of 3.
Okay, I think that is correct. Your electric field is already given. Your area vector, if you write the area vector in the vector form, it will be 0.2 into I. Do we understand this?
yes sir.
That is the only thing you have to understand. Your electric field is given as 3 by 5 I naught I plus 4 by 5 E naught J. You have to take the dot product of these two. You have to dot this with this, and that will be your answer for flux. So your flux will become 0.6 divided by 5 into E naught. That is the answer that I was looking at. Do we understand this? Yes or no?
Yes sir.
Well, that brings us to an end of this class, where we had dealt with electric flux. In the next class, we will be doing Gauss law. Here we have found out the electric flux using electric field. There again, we will find out the electric flux, but using a different thing, a different concept. So see you in the next class. Take care. Have a nice day. God bless you all. Bye-bye.